And then goal two, obviously, we need to make more affordable cars. One of the things that troubles me the most is that we don't yet have a truly affordable car. That is something that we will make in the future. But in order to do that, we've got to get the cost of batteries down, and we've got to be better at manufacturing. And we need to do something about this curve. The cost per kilowatt hour of batteries is not improving fast enough.
So that's what's motivating us to rethink how cells are produced and designed. To make the best cars in the world, we design vehicles and factories from the ground up. And now we do this for batteries as well. So let's get started. We have a plan to halve the cost per kilowatt hour. And it's not a plan that rests on a single innovation, some research project that'll never see the light of day.
I mean, we basically thought through every element of the battery, well, almost every element. There are a few more elements that we won't get to today, but we will get to in the future.
So first, before we get too far into it, let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those terminals, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over 1 meter long in a typical 2170 cell. To explain what's actually going on here, we've identified we've got anode, cathode, separator, positive and negative terminal. Watch what happens as we discharge the cell. Got lithium moving from anode to cathode, and then the reverse. When we charge the cell, lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, no matter what the form factor is. And when we look at what's happened to date, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future. This was an evolutionary step going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal cell design, if we were to do it ourselves, so as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. Supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. We came up with this tabless architecture, basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. This is what we mean when we talk about tabless. We basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see. With simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
The distance that electron has to travel, is just much less. You actually have a shorter path length, a large tabless cell, than you have in the smaller cell with tabs. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. There's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything.
What's elegant and simple is still hard.
People that really know cells, this is a massive breakthrough.
For cylindricals to be able to get rid of the tabs dramatically simplifies winding and coating and has an awesome thermal and performance benefit. And so when we put it all together and go to our new 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase just form factor alone. This is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. It's a video of some of what's going on in the plant. To be clear, it will take about a year to reach the 10 gigawatt hour capacity.
So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. Let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time. One of the most important processes is where it all begins, the wet process of the electrode coating. just to give you all a sense of scale, I'm going to walk through what's in that wet process. You've got mixing where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven where the slurry is coated onto the foil, huge ovens, tens of meters long, dried, and that solvent then has to be recovered. You can see the solvent recovery system. And then finally, the coated foil is compressed to the final density. And when you're looking at this, you're like, wow, that's a lot of equipment for one step, especially when you consider that little speck next to the coating oven is a person. This is serious iron involved in making batteries. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat? And that's what the dry process really is about. You can see it here on a bench top. Literally, powder into film. As simple as that. But if you do scale it up,
Yeah.
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there. But this is a really profound improvement. Again, for people that know battery manufacturing, this is gigantic. We'll probably be on machine revision 6 or 7 by the time we do large-scale production.
Yeah, and beyond the electrode, we continue to innovate on every other process step. So let's talk a little bit about assembly. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion. And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying. And the vertical integration with the machine design teams at Groman and Hybar and others allows us to really accomplish that because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine and remove all of these unnecessary steps. Okay, now let's talk about formation. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principle and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint.
Essentially, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. Basically 4 times better than the current state of the art to the best of our knowledge. I think there's probably room to improve even beyond that. I would actually not have thought this was possible several years ago, that we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. And so this is 100 gigawatt hours supplemental to what we buy from suppliers. Like reduce our weighted average cost of a cell because it allows us to make a lot more cars and a lot more stationary storage. And then long term, expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
So we have a manufacturing system. We've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yeah, basically, with silicon, the cookie crumbles and gets gooey.
And current approaches to solve this, which exist, I mean, we have silicon in the cars that you're all in right now, are involved highly engineered, expensive materials. Now, they're still great, and they enable some of the benefits of silicon. They just don't enable all of it, and they're not scalable enough. And you can see some of the things that maybe you've heard of, SiO, silicon with carbon, or silicon nanowires. I mean, that's kind of the space right now. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
If you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
The anode would cost, with this silicon, and the anode costs $1.20 a kilowatt hour. And how does it work? Start with raw metallurgical silicon, stabilize the surface with an elastic ion-conducting polymer coating that is applied through a very scalable approach. No chemical vapor deposition, no highly engineered, high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. By leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
And when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. People are always talking about oh, what's the cathode going to be? Is it NCA or whatever? The thing to consider is just fundamentally what the nickel, the metals are capable of, and that's what we have on the chart here. Dollar per kilowatt hour cathode of just the metal, using just LME, London Metal Exchange prices, versus the energy density of just the cathode. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt hour. But it's not just about nickel.
In order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. I think we need to have a kind of a 3-tiered approach to batteries, starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, and then a high nickel for long range applications like Cybertruck and the semi. Because something like a semi truck, it's extremely important to have high energy density in order to get long range. If you look at the watt-hours per kilogram at the cathode level of iron, it looks like nickel's twice as good. But when you fully considered at the pack level, everything else taken into account, nickel is about maybe 50 or 60% better than iron. So iron is a little better than it would seem when you look at it at the pack level fully considered. It's not as good as nickel. Nickel is like 50 to 60% better, but it's actually pretty good. Like I said, for intermediate, it's kind of a nickel manganese, relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
And with very little energy trade-off, just enough to have you still want to use 100% nickel for something like a semi-truck, but really not much of a sacrifice at all.
Yeah.
Beyond the metals, because a lot of people spend time talking about the metals, actually the cathode process itself is a big target. 35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. Here's a view of the traditional cathode process. Effectively, if you start at the left and you have the metal from the mine, the first thing that happens is the metal from the mine is changed into an intermediate thing called a metal sulfate, because that's just happened to be what chemists wanted a long time ago. And then when you're making the cathode, you have to take this intermediate thing called metal sulfate, add chemicals, add a whole bunch of water, a whole bunch of stuff happens in the middle, and at the end, you get that little bit of cathode and a whole bunch of wastewater and byproducts.
So we've looked at the entire value chain and said, how can we make this as simple as possible?
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and zero wastewater. And then when you think about the fact that now we're actually just directly consuming the raw metal nickel powder, it dramatically simplifies the metal refining part of the whole process. We can eliminate billions in battery-grade nickel intermediate production. It's not needed at all. We can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. Now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost. The way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
It's important to note that there is a massive amount of lithium on Earth. Lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. Nobody's done this before. To the best of my knowledge, nobody's done this. You know, all the elements are reusable. It's a very sustainable way of obtaining lithium. And we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
Over 10,000 acres. And then the nature of the mining is actually, I think, also very environmentally sensitive in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was.
So we're really excited about this, and there really is enough lithium in Nevada alone to electrify the entire U.S. fleet. And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why. The value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow.
Yeah, I mean, to date it's been done by third parties, but we think we can recycle the batteries more effectively, especially since our batteries, we're making the same battery as the thing we're recycling. So whereas like third-party recyclers have to consider batteries of all kinds.
And just to think about what this actually means, the recycling resource is always 10 or greater years delayed because batteries last a really long time. But eventually, it is the way that all resources will be made available, and that's why we're investing in this recycling facility in Nevada. So we just talked about scaling cathode and recycling. all of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
Great. I mean, there's an architecture that we've been wanting to do at Tesla for a long time, and we're finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things. It starts with having a single piece casting, or a single piece casting for the front body and the rear body. In order to do this, we commissioned the largest casting machine that has ever been made, and it's currently working just over the road at our Fremont plant. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. In order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. In fact, in general, we've got a lot of advanced materials coming for Tesla, new alloys and materials that have never existed before. You're basically making the front and rear of the car as a single piece. That then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. Then somebody said, hey, what if we just make the wing tanks, what if we just make the fuel tank in wing shape? It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. Effectively, the non-cell portion of the battery has negative mass. We save so much mass in the rest of the vehicle than the non-cell portion of the battery. How do you really minimize the mass of a battery? Make it negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. Instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive as well as flame retardant. It effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. This is actually even better than what aircraft do, because aircraft do not do this. We can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car. So it improves the mass efficiency of the battery, and then those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way. It also allows us to move the cells closer to the center of the car. If you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't know why, but it just feels more agile. It's really cool, really major. So 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. Long term, in any cars that do not take this architecture will not be competitive.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. You saw the part removal, it's casting machines, it's the structural battery pack. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
Major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
We're not just talking about cost or range. We've got to look at all the facets. Range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought? What this enables us to do is achieve a new trajectory in the reduction of cell cost. To be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. If we could do this instantly, we would. It just really bodes well for the future and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. What tends to happen as companies get bigger is things tend to slow down. Actually, they're going to speed up.
And they have to speed up if we're going to accelerate the transition to sustainable energy.
So long term, we want to try to make about 20 million vehicles a year.
But I think it's important to point out that when we talked about 3 terawatt hours by 2030, the problem is a 20 terawatt hour problem. So everybody needs to be accelerating their efforts to accomplish these objectives. Doesn't matter where you are in the value chain, there is a ton to do. You need to rethink from first principles how you do it so that you can scale to meet all of our objectives.
What does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. This has always been our dream from the beginning of the company. I even wrote a blog piece about it. I think probably about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
So we have and extreme performance and range, and we should probably talk about the Model S Plaid. We took the latest Plaid out to Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time. We're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise. And you can order it now, available basically end of next year.